if z is a complex number, then we have to find the number of common roots between these two equations. Now, this is a problem from Singhese and it was asked in JEE Main 2024. And here basically, in order to find number of common roots, first we'll solve this second equation. Right, we'll try to find all the roots of this cubic equation and then we'll try to see whether those roots are also the root of first equation or not. Also, in order to solve any cubic equation, or in fact any polynomial equation of degree more than 2, whether it is cubic, biquadratic, and so on, one root we need to get using heat and trial method, and then from there we can get the remaining roots. So if I have to solve the second equation, one root we have to find using heat and trial. And for using heat and trial, mean constant term is 1, so we have to check with either +1 or -1. Right? We need to check only with the factors of constant term. So in place of z, if I substitute -1, because z equals to +1 will not work, right? We have all the positive, we have all the terms with plus sign in between, so it will not have any positive root. So let us check with z equals to -1. In place of z, if we substitute -1, the first term will be -1 plus 2 minus 2 plus 1. So it will become 0. That means z equals to -1 is a root of this cubic equation. And if z -1 is a root, this will imply that z plus 1, this will be a factor of this cubic. Right? For a cubic, we can have three linear factors. One of the linear factors will be z plus 1. So now we'll try to split the terms in such a manner that we can create z plus 1 as common factor, so that from there we can get the quadratic factor. So given equation is z cube plus 2z square. Now because we need z plus 1 as factor, so 2z square I'm writing as z square plus another z square. So that from first two terms we can get z plus 1 as common factor. Now again we have z square next term, and if I need z plus 1 as common factor, next term must be z. So that from these two again you can take z plus 1 common, and because we had 2z here, z we can write as z plus 1, this equals to 0. And now you can see that you can take z plus 1 common from all of these three terms, right? We can take z plus 1 common from here, from this one, and from these two terms. I mean, if you want, you can divide this cubic by z plus 1 and then get the quadratic factor, but this will be another easier method of finding the quadratic factor. So from first two, you will get z square. From next one, you will get z plus 1 equals to 0. And now clearly you can see that for this equation, if first term is 0, z equals to -1, this we have established earlier. And if z square plus z plus 1 is 0, from there you will get the roots as omega and omega square, where omega is the imaginary cube root of unity, omega and omega square. So basically for the second equation, these are the three roots, -1, omega and omega square. And now we need to check -1 we got from z plus 1 and omega square from this next quadratic equation, z square plus z plus 1 equals to 0. Now we need to check whether these numbers are also the root of first equation or not. So let us check one by one. If I take z as -1, then -1 raised to odd power, that will be -1. -1 raised to even power +1 plus 1. Right? So we are getting left hand side as 1. So -1 will not satisfy. Right? -1 cannot be common root because it is not root of first equation. If I take z as omega, let us check with z equals to omega. Remember, omega cube is 1. So if I take z as omega in first equation, the left hand side will be omega raised to 1985 plus omega raised to 100 plus 1. Now, because omega cube is 1, we can divide this by 3. And if I divide this by 3, the remainder will be 5 by 3. So remainder will be 2. That means this term will become omega square. And next term, omega raised to 100 will be same as omega, because omega raised to 99 will be 1 plus 1. This will be 0. That means omega is a common root between the two equations. Omega is a root of second equation and it will also satisfy the first equation. Similarly, let us check with z equals to omega square. Now, if omega is a root, omega square, this will also satisfy, because in place of z, if we write omega square, then this term will become omega square raised to 1985. When you divide by 3, the remainder will be 1. So first term will become omega. And similarly, this term, second term, omega raised to 200, omega square raised to 100. And when you divide by 3, then you will get omega square. 198 is multiple of 3. So this will become omega square plus 1, which is again 0. So as you can see that z equals to omega and omega square, both of these numbers will satisfy the first equation also. So therefore, this is also a common root, right? So for second equation, there are three roots, minus 1 omega and omega square. The two roots omega and omega square will also satisfy the first equation. And therefore, the number of common roots for this system of, for these two equations, this will be 2. And hence the correct answer is second option, right? So this was not a difficult problem again, just solve the second equation. One root you need to find using heat and trial method, and once you get that root, the other two roots are omega and omega square, and then we need to verify from the first equation. So only the other two roots omega and omega square is satisfying the first equation, and therefore those two are the common roots, and hence the correct answer for this problem is second option.